Everybody. Welcome to this webinar brought to you from Geobear. So I'm Alistair Willis, Marketing Director for Geobear in the UK and essentially the host of this webinar. But with us today is our Vice President of Engineering, Andy Lee. And as you'll know, because you've signed up, this webinar is actually about clay shrinks well behavior and its treatment with Geobear solutions, essentially using geopolymer. So there's a chat box there. Good morning, Gerard. There we go. You can hear us. That's good news. And there's currently over 400 people online. So great to have everyone involved. And obviously, this is a very relevant topic this year due to the dry weather and what's happening with clay. So I'll stop mumbling and hand straight over to Andy, who's going to run you through the presentation, and then I'll reappear at the end, where there'll be a Q&A session. So within the chat, I'll switch that over to Q&A sort of halfway through, and then you can add your questions there. So good morning to everyone that's in the chat, and I'll hand over to you, Andy.
Okay, thank you, Alistair. Let's get into the presentation. So just a little bit of an introduction as to who Geobear are. We are a global leader in non-disruptive solutions for foundation and infrastructure settlement and substance problems. Global business established in 1983 in Finland. Company was known as Eurotech until 2017 before global rebranding as Geobear. UK business was established in 1989 and currently have offices in Wolverhampton, Hatfield and Winchester. We have a full in-house design team, but we also work with third-party consulting engineers and material testing labs. Overall, this technology has been applied to more than 250,000 projects worldwide by Geobear and former licensees and franchise holders of the Eurotech brand. So where are we based? I'm in the UK, where we have operations in UK and Ireland, Sweden, Finland, Poland, China, in the Gulf, in the UAE, and in the United States. In terms of the sectors we operate in, it's highways, commercial sector, warehousing, residential properties, power and utilities, airports, ports and harbours and railways. And most of these sectors, if their structures are built on clay, will be affected by seasonal movements. So this is about the nature of the geology rather than the structure on top of the geology. So let's go through the basic principles of clay shrinks well. Some of you may be very familiar with this, so just bear with me. So all clays are susceptible to volume change due to changes in moisture content. Reducing moisture contents leads to shrinkage or subsidence, and increasing moisture content leads to swelling or heave. The degree of volumetric change for a fixed change in moisture content is due to the differences in the clay mineralogy, and there are three principal types. We have kaolinite, illite, and montmilionite. The most expensive clay mineral is montmilionite and kaolinite the least. It's the relative proportions of these clay minerals in a clay formation, such as the London clay, which determine exactly how expansive it will be. And there's a drawing here of the mineral structure of a typical clay soil. And what you should notice really is the way in which the sheets fit together. These are the sheets of silica and the sheets of alumina, which are the building blocks of clay minerals. And for montmilionite, there is a very weak bond between the silica sheets. And that weak bond allows water molecules to absorb into the gap and cause volumetric expansion. It is far more difficult for water molecules to get into the gaps in other types of clay minerals because the bonding between the sheets is much stronger. And that's the fundamental reason why some clays are more susceptible to swelling. So determination of the detailed clay mineralogy in the lab is a complex task, and so index testing was developed to quickly determine the swelling potential of a soil. We have our Atterberg limit tests. These are simple soil mechanics tests carried out in the lab to determine parameters for the classification of soils. The tests determine the following limits or indexes. We have our liquid limit, which is a minimum water content at which a soil will flow under small disturbing force. The plastic limit is the minimum water content at which a soil can be deformed plastically. And we have the shrinkage limit. This is the moisture content at which no further volume change will occur. And the difference between the liquid limit and the plastic limit is called the plasticity index. I think these are key parameters for identifying the risk of shrink swell in a clay soil. There are other tests that you can do, and you can measure something called the activity, and this is defined as the ratio of the plasticity index to the percentage weight of clay-sized particles, as determined via sedimentation test. And then we have the modified plasticity index, and this is the plasticity index multiplied by the percentage weight of silting clay-sized particles, as less than 425 microns. There are other tests you can do, odometer testing and swell testing, and these determine the following parameters. The coefficient of volume change, MV. This is how much a clay soil will compress for a given load, with a corresponding decrease in moisture content. And the coefficient of consolidation, CV. This is how long it will take a clay soil to compress for a given load. And swelling index, the rate of expansion of a clay during unloading and rehydration. So these are a little bit more advanced soil mechanics tests that you can do, which may or may not be required on any particular project. So let's just have a quick look at the Casagrande classification chart. This is a very useful way of plotting your plasticity index and your liquid limit results. You can plot them on this chart. And if those points plot above the A line, which is the diagonal line moving across the page, you have a clay soil. If they plot below the A line, you basically have an inorganic silt. And silts generally do not display cohesion. They may display dilation, but they don't display cohesion. So those soils which are presenting a risk of shrink swell are going to be plotting above the A line. And they're going to be plotting as I look at the screen, on the right-hand end of that line, in the zone identified as inorganic clays of high plasticity. This is where your results are likely to plot if you've got a high volume change potential. So how does changing moisture content affect volume? This graph is been produced just to give a quick overview of what happens as you increase moisture contents. So with moisture content on the x-axis, we start at a point where changing the moisture content doesn't really change the volume of the soil, and that is for moisture contents less than the shrinkage limit. So a clay below the shrinkage limit is going to be very hard and brittle. It will show elastic behavior. You cannot deform it plastically. As you now move from the shrinkage limit up towards the plastic limit, the soil will behave more elastically, but it will not plastically deform as you put load on. And there's a small increase in volume. Now, as the moisture content grows and you move towards the liquid limit, the volume of the soil will continue to increase due to the increase in moisture content. And so you get an increase. So the larger the difference between the liquid limit and the plastic limit, the greater the volume change is likely to be. And the theoretical range of volume change between 5 and 18%. So low plasticity clays have a relatively small volume change potential, and high plasticity clays have a relatively high volume change potential. Now, I'm going to talk a little bit about desiccation. And certainly in the UK and in the insurance sector, a lot of weight is still put on a publication done by Driscoll back in 1983. And he identified at what point, based on your lab testing, could you say the soil is significantly desiccated? By desiccation, that really means, does it have a lower than normal moisture content? So he sort of came up with a definition which was sort of stuck for many years. And he said that desiccation could be presumed to commence where the rate of change of moisture content and hence volume with increasing suction increases notably. This point could be taken to be approximately at a suction factor of PF equals 2, which is 10 kPa in terms of pressure. Similarly, significant desiccation could be taken to have occurred when the suction is sufficiently large that on its release, a low-rise building could be lifted. Typically, this suction would have a value of PF equal to 3, which is a suction force of 100 kPa or 100 kilonewtons a meter squared. So what he was essentially saying is that in order to have a soil that appears to be significantly desiccated, it's such that it would have an impact on a structure and could make it move. And that's the key thing to take away. When the suction forces are effectively less than the weight of the building, it will not lift the building and it won't move. But he defined these 2 points. What is really interesting is when you get less moisture content to liquid limit ratio less than 0.4, you start generating much greater suction forces. So on this graph, I've plotted 2 points at a moisture content to liquid limit ratio of 0.5, and you see that the suction force here is 10, so very relatively small or negligible. And as you move to the left-hand side on the graph, we have reducing moisture content with a constant liquid limit till you get to the point of 0.4, where the suction force is 100 kPa. Now, as you move and the soil gets drier and you start moving towards the plastic limit and then ultimately the shrinkage limit, the suction forces increase significantly and there's an exponential relationship. So that when the moisture content to liquid limit ratio is 0.3, the suction force is now 1,000 kilonewtons a meter squared. So that shows you the impact as a clay soil gets progressively drier. The suction forces, or those forces which are causing it to consolidate, are increasing significantly, and it's not a linear relationship. So very dry soils have extremely high suction. I just want to talk briefly a little bit about persistent water deficit. This is slightly out of sequence in the general presentation, but I just want to mention what I mean by a persistent water deficit. Now, in clay soils, the moisture content will vary seasonally, and it will vary seasonally due to precipitation and evaporation. So in the summer, there's more evaporation and less precipitation, and in the winter, there's more precipitation and less evaporation. And in a normal soil, maybe at surface, maybe covered with grass, the depth of those seasonal variations may extend to about a meter, at best, about a meter. Now, when there are trees present, they have a much greater water demand than grass, and their roots penetrate into the soil to a much greater depth. And that means they will take moisture from the soil at deeper levels. And if you have a mature tree that's been in situ for quite a long time, if the amount of water the tree's taken from the soil is greater than that return to the soil during the winter, then you can develop what's called a persistent water deficit. So there's basically effectively the trees pumping out more water than is being returned due rainfall in the winter. And you often see this feature of deep desiccation. So when you measure those moisture content to liquid limit ratios in the presence of trees, you can find that you have significant desiccation as previously defined at significant depth, and that's due to the effect of the trees. I'll be talking more about trees later on in the presentation. I just thought I'd introduce this to a general concept, because interpreting site investigation data can be confusing, particularly if you sample sites in the winter. You can find deep desiccation underneath what appears to be soil that's not desiccated, and this is because of the effects of persistent desiccation at depth. Seasonal movement in clay soils. So seasonal movement of buildings and structures on expansive volume change clay soils is well-known phenomena. It's reported as the #1 natural ground hazard in the UK by the BGS. The timing of the movement of buildings on expansive clay soils is closely linked to what's called the soil moisture deficit, as reported by the Environment Agency via their Met Office department. And there's some graphs here that show a general sort of sine wave of the variations of soil moisture deficit with the seasons, sort of peaking during the sort of late winter, early spring, and then dropping down to minimum values towards the end of the summer into the early autumn. And that sort of sine wave continues on a cyclical basis. However, it's not always the same. And what you find is that the amount of soil moisture deficit will vary depending on the climate. And there's some graphs here that show the current soil moisture deficit for what is called a grass with deciduous trees. And just to explain what the deficit means, it means is that the soil, when the soil is fully saturated and is at field capacity, the soil moisture deficit is 0 because the soil is fully saturated. And so a calculation is done in terms of how much moisture has been lost from the soil, and that's converted into a depth number. That's why soil moisture deficit is measured in millimeters, and it equates to the depth to which the soil has lost moisture. It's not the depth to which the desiccation is stopping. It's just a relative measure as to how dry the soil is. And you can do it for ground that's covered with trees and you have one deficit, and you could do it for ground covered with grass and you get a lower deficit. And this is a function of the depth of the roots. But essentially what we're seeing this year in the UK in 2025 is a pattern of soil moisture deficit that is very similar to 2018 and also 2022, when there was a notable increase in insurance claims for building damage due to clay subsidence. Interestingly, the data for last year, 2024, where we had quite a wet year with quite a poor summer, the soil moisture deficit didn't get anywhere near the levels it is today. So, and you can get this data from the Met Office and look at it over many years, and you can see these variations. But it would appear we're certainly in an event year, as it's described by the insurance industry. And this just shows that if you do PLM monitoring, this is precise level monitoring of buildings, you find that the up and down movement of the buildings is almost exactly the same as the up and down movement of the soil moisture deficit. And that's because the changes in moisture content in the soil are causing changes in suction pressure, and those changes in suction pressure either cause the soil to consolidate, or they cause the soil to expand. So practical observations NHBC publish guidance about building near trees. It's their chapter 4.2 in their guidance documents. I'm just going to run through a little bit of an overview. So if you look in the NHBC guidance, they use the term modified plasticity index to essentially do a risk assessment on likelihood of volume change movements. And they rate high volume change potential for soils where the modified PI is above 40%. They rate it as medium volume change potential between 20% and 40% modified PI. And they assess volume change potential as low between 10 and 20% modified plasticity index. And also within their guidance, NHBC provide recommendations on minimum foundation depths to avoid foundation movements due to seasonal variations in moisture content. Now, the depths are based on the volume change potential as described. And so for high volume change potential soils, they have a minimum foundation depth of 1 meter. For medium volume change potential soils, they have a minimum depth of 0.9 of a meter. And for low volume change potential, they have a minimum depth of 0.75 of a meter. So the theory is that as long as you get your foundations below that level, depending on the modified plasticity index, the building should not suffer from seasonal movement because you're below the level that moisture content changes are significant enough to cause damage. However, there's a large number of houses that were built prior to the NHBC guidance being in place. A large number, certainly in the UK, and quite a lot of these properties have very shallow foundations. And what you find is that if you cast a foundation above the recommended minimum foundation depth, there's a high likelihood that you'll see building movement. And this is quite a common occurrence. And not only that, damage is often caused by differential movement. So you may have a property where some of the foundations appear to be at the right depth, and maybe there's an extension that was put on later and that has very shallow foundations. And so there's the opportunity then for one part of the building to move at a different rate to another part of the building. And that difference in the rate or the amount of movement causes differential damage. And this is really quite a common occurrence, particularly when there's add-ons to buildings that don't have adequately deep foundations, or with just very old buildings that never really had deep foundations in the first place. But the situation becomes a lot worse when there are trees near to those buildings with either shallow or deep foundations. Now, often if you have an older house, the trees that may be near to the house might not have been present when the house was built. So if you have a house that's 200 years old, it's entirely possible that a tree could have self-seeded within a near distance to your property. And then you have a new tree that's appeared and grown over the last 30 or 40 years. And that's now going to affect your foundations. And the NHBC recognise this, as most people do in this line of work. And so the normal remedy is to have deeper foundations where there's trees. And guidance is published by the NHBC, which sort of tells you how deep the foundation should be for a given volume change potential, either medium, high or low. And also for the type of tree and the distance and height of the tree relative to the building. And there are design charts which you can look up on their website, and they'll tell you how deep the foundation should be. That there is a proviso there that those guidance stops at about 2.5 meters. So if a large tree is very close to a building, you may find that the depth and height ratio relative to the building is not covered by the design chart. And in those situations, they refer the customer to contact an engineer for guidance. And so in my experience, most of the trees that cause the damage are probably closer than the NHBC guidance covers. So that requires you to do additional investigations to determine the depth of desiccation, as I mentioned previously. I'll be talking more about trees in a minute. Expansive clay formations. So most, if not all, of the highly expansive clay formations in the UK are fissured clays. So these are clays that will be deemed to be high volume change potential. I will caveat and say that most clay formations have the potential to cause shrink swell problems. Even low plasticity glacial till and other formations like that, alluvial clays can show shrink swell behavior. For the purposes of this conversation, I'm going to focus on fissured clays, because the vast majority of claims, not all, but a significant percentage of claims due to subsidence damage are on these particular formations. And of those formations, London clay is the single most commonly occurring strata underneath buildings which are suffering from clay subsidence. And that's a combination of the fact that it has a high plasticity index, and it's also where there's a lot of houses. So the correlation between where the houses are and where the clay is, it sort of centres on London. But these formations do crop up generally in the southeast of England. So this is a close-up look at the London clay in an excavation. So what you notice when you look at the actual formation in a cutting or an excavation is that the clay itself doesn't really look like a clay. It looks quite blocky. It looks quite fractured, and you can see lines of discontinuity within the actual clay. And this is natural features, often called joints, and they're formed due to the diagenesis of the clay as it was laid down and compacted over millennia, and as it was raised near surface due to tectonic activity. These fissures open up under stress release, and so there are natural and common phenomena in these types of over-consolidated clays, which are called fissured clays. Here's a borehole sample showing some vertical and horizontal fissures. Now, there's some interesting work done by a guy called Height, who was looking at the structure of discontinuities within London clay, and he took some core samples from a London Underground project, a tunnelling project, just to assess the geotechnical properties of the London clay. And he so happened to put some clay cores into a CT scan, such he could look at the internal structure of the clay. And what he found is that these discontinuities and fissures are present everywhere throughout the formation. And in the top 5 meters of the formation, they are typically spaced at less than 12 millimeters. And so they're regular fissures in all 3 directions. And so it's just a natural phenomena. And this is why we call these types of clays fissured clays. So there's an interesting facts about fissured clays. And this is really quite important in terms of why I think certain formations really show significant movement. And fissure clays essentially have a dual porosity and permeability, with a low permeability intact clay blocks separated by an interconnecting fissure system of relatively higher permeability fractures or fissures. The combination of these two permeability systems is referred to as a bulk permeability in this presentation. So that is the combined permeability of both the intact clay and the fissuring system. It is very difficult to measure the permeabilities and porosities of individual clay fissures themselves. Now, these clay fissures can be, less than 0.1 of a millimeter wide, but they do get wider as you get nearer the surface. And in a particularly dry year, they can be really quite wide and open up to a few millimeters in width. But nonetheless, it's very difficult to measure the permeability of a fissure. It can be done using gas testing in a lab. It is possible to do it. It's not something that's easy to do in the field. And due to this, I was interested to know what the relative permeability is of the fissures versus the intact clay. So we can measure the full bulk permeability, and we can measure the permeability of the actual individual blocks if we take them to the lab and we do a triaxial permeability test. We can measure the permeability of intact clay. And we know that if we have intact clay, it's generally very impermeable. And we use recompacted clays, which don't have fissures, to create landfill lining systems, or they're used in the cores of dams. And most people know they have very low permeability when there's no fissures, typically 10 to the minus 10 meters per second or lower. But I was interested to know the relative difference between the two. So we developed a simple model to try and analyze how would the permeability within a fissure clay vary. The reason that's important is because it's going to control the way in which moisture is lost and gained by the soil. So if we think about a fissure clay model and imagine we have a clay which is formed of cubes of intact clay, which have low permeability, and they're surrounded by an interconnecting fissure system of horizontal and vertical fissures in 3 dimensions. You can imagine a system of 2 different types of permeability: the permeability down the cracks and the permeability through the solid clay. And so you can actually put that into a spreadsheet, and you can sort of use some basic assumptions regarding how to calculate the permeability of a fissure based on Hazen's principles. And you can generate a simple model that indicates if you know the permeability of the intact clay, and if you know the bulk permeability of the total clay from field measurements, by subtraction, you can work out the permeability of the fissures. And what you find is that the difference between the permeability of the fissures in this model, and I accept it's a simplified model, are between 5 and 50 times higher than that of the intact clay. So this is indicating there is a difference in permeability between the solid lumps of clay and the fissures. And so the fissures provide a pathway, or a quicker pathway, for moisture to enter a soil and leave a soil. Whether that's in the liquid phase or in the vapor phase, it's a higher permeability. So moisture is more likely to enter and leave a soil via the fissures than via the intact clay. And so if you can change the permeability of the fissures by grouting using an impermeable geopolymer, which is based on polyurethane technology, you can change the overall bulk permeability of the clay by essentially just grouting it all up. Now, this has been tested in the lab, and a paper prepared by Boozy et al. 2010 measured the geopolymer permeability and determined that the actual geopolymer itself is in fact impermeable, I mean, it's based on polyurethane technology, like a plastic, so it has very low intrinsic permeability. And he observed that if you inject it into a clay core and then measure the gas permeability of the clay core, obviously before and then after, there was a reduction in permeability due to grouting of a factor of about 50. And that happens to nicely coincide with sort of Fisher clay model. So this is indicating to me at least that we can reduce the permeability of a clay by a factor of about 50, and that should reduce the rate at which moisture can be gained or lost from a clay soil. As a fundamental basic principle. And based on that, so how does changing permeability affect clay subsidence? So with the objective of geopolymer treatment to reduce the bulk permeability, as I said, by a factor of about 50, this will reduce the rate at which water is lost from the clay and slow down the rate of seasonal movement. And this is because the time of consolidation, T-consol, is inversely proportional to the coefficient of compressibility CV, which is itself is proportional to the permeability K. Now, the relationship between the time of consolidation, the thickness of the soil sample, the coefficient of consolidation are shown in these equations, which are taken from Tomlinson, but they are standard soil mechanics equations, and they are well known and used for calculating the rate of consolidation of foundations under load. And a clay soil under suction forces is essentially the same as a clay soil under a load. Instead of it being under a vertical load, it's under an isotropic shrinkage load or pressure. So suction forces in clay soils are intrinsically isotropic, and they cause the clay to consolidate under that force. It's not due to the weight of any building squeezing the clay. This is purely due to the internal suction forces. So you can sort of calculate what those changes are going to be by reducing the bulk permeability, which is one of the main ways in which geopolymer can be used to reduce the rate of settlement and also reduce the rate of heave. But it's not the only thing that's going on. So the idea for a geopolymer treatment zone, so the geopolymer is injected into the clays with the objective of penetrating the fissures of the clay. It's not necessarily going to go into the clay if the clay itself is very hard. It's going to go into the cracks in the clay. Now, grouting of the fissures will substantially reduce the bulk permeability by a factor of about 50. And the depth of treatment is extended below the zone of desiccation as previously described. So the idea is we need to fill in all the fissures and get the treatment down below the level of significant desiccation. And that will essentially sort of freeze the soil in that sort of condition. But that's not the only thing that's really going on. And we really need to understand what is the impact of roots and rootlets to really understand how and why clay shrinkage really occurs. And in this picture, you can see there are different types of roots on a tree. There are lateral roots and there are structural primary roots, sometimes called tap roots. And these provide the actual structural strength to hold the tree in place. But the moisture from the soil is actually taken by the root hairs. And these are the very fine outgrowths at the end of the lateral roots. And it's important. Here are some interesting facts about tree roots. So looking at that picture. So the root system of woody plants comprise perennial woody roots and many short-lived fine roots. So the woody roots, these are the lateral roots and the tap roots, and they are covered in effectively bark, and they're pretty much impermeable, those roots. The large roots comprise most of the root biomass, but account for little of the total root length in contact with the soil. and the vast majority of water is abstracted from the soil via the short-lived fine roots and root hairs, which are normally less than 2 millimeters in diameter. And so water is removed from the soil via the root hairs and transpires from the leaves of the tree following negative water potential. So there's some really important things here to grasp. And one is that the moisture is taken from the soil by the finest roots, not by the main tap roots that you can imagine. And those fine roots are they are short-lived. What does that mean, short-lived? It means that every year when the leaves fall off the trees, for broadleaf trees, the fine roots actually die because there's no need for them to exist, because the tree's not taking moisture from the soil. Because if there aren't any leaves, the tree can't get rid of the moisture. It can't transpire from the surface of the leaf. So there's really, if the fine roots were taking moisture during the winter, the tree would just get very large. It couldn't lose it because there's nowhere for it to transpire from. And the way, when you look at trees themselves, they are a giant groundwater pump, and water is lost as it moves from high potential to low potential. And so the suction forces on the leaves of trees are very low and measured in the order of megapascals. So -2 megapascals would be a typical water potential on the surface of a leaf. And even in a desiccated soil, there may be a negative soil potential of -300 kPa, but that's much greater than -2000. And so water is drawn from the soil to the leaf, and it transpires from the leaf into the atmosphere. That's how moisture is lost from the soil by a tree. The next thing to think about is root penetration. As I said, every year the fine roots on trees die, and that's the same is true for conifers as well as for broadleaf trees. So the very finest roots die off every year anyway. Now, root elongation, or the growing of soils, is generally limited by a combination of mechanical impedance and water stress. So this is the actual growing of the fine root hairs we're talking about here. So root elongation is typically halved in reed-packed soils with cone tip resistances in the order of 0.8 to 2 megapascals, and that's equivalent to a CU range of about 100 kPa in the absence of water stress. So the harder the soil, the more difficult it is for the fine roots to grow through the soil, which is sort of intuitive. Root elongation is also halved by matrix potentials drier than about -500 kPa in the absence of mechanical impedance. So the drier the soil, the more difficult it is for the root to grow through it. And this is due to the way in which fine roots secrete moisture to do the actual boring. So this suggests that the mechanical impedance is often a major limitation to root elongation, even under moderately wet conditions. So the point here is that if you have a tree and every year the fine root hairs die in the winter and grow back in the spring, if you can, and they're going to grow through the bits of the soil that present the least resistance, because they can't grow through hard soil, they're going to grow through the fissures. So it's more likely that the fine root hairs and the roots are going to grow through the path of least resistance, and any soil that has got discontinuities or fissures, the roots are going to tend to prefer to grow through them. And if you can fill those fissures full of hard polymer, then the roots are not going to find it easy to grow back again the next year. In fact, they're going to find it almost impossible, and they're going to basically grow in a different direction where the resistance is less. Just that's how roots penetrate. So showing that in a cross section, imagine you have a fissured clay and it's got roots growing through, or root hairs growing through those fissures. What is the impact if you fill those fissures full of polymer? Is this. So you effectively surround the roots in situ in the clay with polymer, and that is going to do a couple of things. It's going to prevent them from taking moisture because geopolymer is impermeable. It's also going to reduce the availability of oxygen and effectively fossilize the roots, let me put it that way. And they're not going to find it easy to grow back again into this zone the next year because polymer's now in the way. And those root hairs will just grow in areas where there's least resistance or less resistance. I've got an interesting picture here to briefly show you of some roots actually in the fissures of a London clay. Just to show you what I mean, that you can see here there's a root clearly growing along the fissure, which is shown in the grey colour. And this particular sample was taken at a depth of about 3.5 metres. So it just shows that if there are fissures present, then the roots are going to want to prefer to grow along them because it's easier to do that. Okay, so to summarise the impact on roots, water from the soil is absorbed through the root hairs, which are the filamentous outgrowths near the tip of each root. The structural strength of a tree is provided by the main taproot system from which the rootlets and root hairs branch off. It is thought that injection of geopolymer impacts the root system in two ways: encapsulation of the rootlets and root hairs by impermeable geopolymer and prevents them from breathing and drawing moisture. Heat stress from the geopolymer reaction, because the injection of geopolymer is exothermic and generates a short-term increase in soil temperature to around about 200 degrees centigrade. That is also going to cause significant stress on the root, and it's unlikely to survive that type of temperature. These combined impacts are more likely to fossilize the root hairs and the thin rootlets, so preventing future moisture loss. The main taproot system is not likely to be affected, so the tree will remain stable. The trees will then send rootlets in alternative directions to seek out moisture. Here's a quick picture to show what I'm talking about. Here is an excavated fissure that was filled full of polymer. What this is like we've excavated this lump of geopolymer from the soil that was injected into the fissures, and you can see on the surface of the fissure very fine root hairs. And there was no organic material left in these root hairs. They've been completely converted into geopolymer, just to show as an example. So a brief case history in the interest of time. Here we're looking at a semi-detached house with a row of trees behind it on London clay. And we did some treatment here on this particular property on the rear elevation. And we did a partial treatment. So site investigation was available from October 2020 and 23, such that a comparison could be made of the seasonal moisture content and the shear strength variations could be done to predict the change in suction forces and associated subsidence. The results showed a clear correlation between increasing moisture content and reducing shear strength in the top 1.5 meters. So as the soil dries out, it gets stiffer. As the soil gets wet, it gets softer. The change in moisture content was up to 4% in the near surface, with a corresponding change in shear strength of up to 70 kPa. So changing moisture content changes the soil stiffness. And this is another way of identifying desiccation, is to look for areas where the soil strength is higher than the average or against a control borehole. It's another way of indicating desiccation, not only from the liquid limits and the moisture contents, but also the shear strength is a bit of a giveaway. Here shows a plot of moisture content and a plot of seasonal variation in moisture content. What you can see, particularly on the graph on the right hand side, is the red line is the sort of the summer conditions, if you like, showing uniformly stiff soil, of 140 kPa at all depths, and yet on the same site, measured during the summer, so in the winter, the shear strength dropped off tremendously to around about 70, 75 kPa. So this change is entirely due to moisture content variation. Just the moisture being taken from the soil was affecting the shear strength of the soil. Now, you can build a settlement model if with the available site investigation data. And the way a settlement model works, it calculates the suction forces that are going to be generated due to changing moisture content. And by making assumptions about the coefficient of compressibility MV, you can calculate the layer settlement if you construct a layer settlement model. And you can sort of predict how much settlement you would get or how much heave you would get based on a known change of moisture content. And on this particular model, there's a prediction of about 21 millimeters of movement based on the change in moisture content. And that was against an actual downward movement of roughly the same number, which is shown on the following graph. So here, what we're talking is a prediction of this change in settlement of about 20 millimeters. This directly corresponded to the change in moisture content that had been measured. Now, you may be wondering what's happening over here, where we have a downward movement and then a rebound, and then we have a leveling off of movement. And on this part, there is a further downward movement. Now, the data is not complete. There was a data gap, and I've extrapolated between these points and these points. But the reason for the downward movement here is this part of the structure from where these measurements were taken had not been treated. So it shows the difference between full treatment and a partial treatment, that the relative amount of movement is different. And that's purely due to the impact of the geopolymer. There's been no other changes, no change in the trees, nothing. The only change was the presence of geopolymer or not. Getting close to the end of the presentation, I want to leave a little bit of time for questions. General characteristics is the CO2 footprint of geopolymer solutions is generally lower than traditional cement-based options, maybe by about 50% in residential cases. It is inert. We've had it tested for leachate properties. It is safe to use over aquifers. It doesn't generate any harmful compounds in the dissolve phase. We've measured it in the liquid phase during our injection process. Even in the liquid phase, we've found that no harmful compounds are leached out into groundwater during the reaction process. Durability, system has a service life of 60 years according to the BBA. And here are some references. And I've been through that very quickly at the end to leave a little bit of time for questions. I can hand you back to Alistair.
Great job, Andy. Thanks for that. Hopefully you all found that interesting and hopefully enlightening. And there is a lot of questions. So I'm going to switch over to the questions and let's get cracking. Right. Okay. So I'll just display these on screen if I can. Right. So there we go. Matthew, this I think was one of the first questions. We may have answered this as you went through, Andy, but with tests, I'm led to understand the swelling tests are very expensive. What's the most?
Yeah, it's not normally necessary. You can assess the risk of movement of buildings just using liquid limits, Atterberg limits, which are relatively inexpensive. There's no real need to do swelling tests. You can assess a normal lab test data to work out the risk and also calculate the actual movement.
Okay, and Ranj, please address rye foundations in clay soils in close proximity. I think we may have gone through this because this was actually before the presentation started, so let's just skip over that one. If we could try and keep these answers as brief as possible, then
I'll try.
Can you explain the difference between plastic and elastic deformation?
Yeah, I can. Plastic deformation is a permanent deformation. So think about squeezing something and the shape changes permanently. That's a plastic deformation. Elastic deformation is when you put pressure on, it deforms, but it springs back again to its original position. That's elastic deformation.
Yes, and Matthew, again, we probably covered. Matthew says desiccation or over consolidation. Discuss. Not sure what the question is.
I'm not sure about that question.
Yeah.
Desiccation is a change in moisture content against a traditional background. So even over consolidated clay can be desiccated. It's a relative thing.
Okay. Jack, thanks for the question. How can seasonal shrink and swell impact the stability of slopes and embankments constructed using clay soils? If the slope is displaying,
yes, it does.
Yeah.
Yeah, we've seen this on sort of network rail projects, that if you have a clay embankment that's shrinking and swelling, that change in volume can affect the track bed performance due to the vertical movement. Now, clay shrinkage movement is a volumetric change, so it changes in all 3 dimensions. But for most people in houses, it's the vertical dimension that's most noticeable. But yet you can use it. It's exactly the same principles. It's to reduce the rate at which moisture is lost and to deal with any offending tree roots. So the same principle apply to any structure.
Okay, good stuff. This one from James. Thanks, James. So we've got a single story extension near trees, shrinkable clays. Footing should have been 2 meters deep. They're only constructed 1 meter below ground level. Will problem be solved if trees are removed? How long after they're moved will it cease?
Well, if you remove the trees, then I pointed out this earlier, there could be persistent desiccation present. So if you do cut down the trees, then expect to see long-term heave. And so the ground will rise and keep rising. So exactly whether that is too much heave, that depends on the site in question. But if you remove the trees, you're likely to get some heave.
Okay, Jamie, great to have you here. Jamie, 2 questions. Will we get a copy of the slides? Yes. Well, I'm going to send a recording, actually, of the webinar. I think that's the best option. And does Driscoll equations apply only to London clay or any clay? The Driscoll equations are based on the London clay, and they are most appropriate to use for the London clay. And as a guide, I think it's a reasonably conservative approach to use. The actual suction ratio is different for different types of clay, but that's a level of complexity which Driscoll didn't give a number for. Yeah. Andrew asks about crowning or pollarding trees and the impact on persistent water deficit. Well, I think it would do, actually, because if there's a persistent water deficit under a tree and you then pollard it or crown it, effectively the tree will take less moisture from the soil. So that means there's more chance that the persistent water deficit will reduce because the tree's not maintaining it. Therefore, you'll get heave or a little bit of heave. Whether the amount of heave you get depends on how extensive the pollarding is. Okay. Helen, please comment on very dry summers followed by very heavy raining. Can this wash away soil fines and change volumes in that manner, especially on slope ground? Well, yeah, I mean, very heavy rain on sloping ground can cause erosion. That's just surface water runoff erosion. Washing away fines is more common in granular soils. So yes, if you've got a granular soil, then heavy rain will wash out the fines. In a clay soil, this is less likely because the fines themselves are held together by the cohesion of the soil. Okay, now a question from Brian Bell. Hi, Brian. Where extremely highly sensitive shrinkable clays known to exist for depths greater than 5 meters, which Geobear injection system is appropriate to arrest subsidence and cracking? Well, I would say to Brian, who I know, hello, Brian. Yes, I think the normal geopolymer system is appropriate for any depth of treatment. It just depends on the particular case we're looking at, but there is a Geobear system specifically designed for clay shrinkage. And that is the one that we apply in all cases. Yep. And then Joanna, good to have you here. Do these depths quoted take into account the presence of trees or nose trees? I think that was back on the NHBC. Yeah, they're no trees. They're the no trees depths. The trees depths are significantly deeper, and you can look at the NHBC tables to get those depths. Okay. So I might be skipping a few questions here because I think they might be answered in the slides. What about this? Simon, I have a situation where foundation has moved sideways. There is a large tree 10 meters away. How would Geobear treat this problem?
I think we'd have to look at it as a specific case to see the zone that needs treatment. There is always a potential for sideways movement where there's desiccation because it's a volumetric change. So you normally see more vertical downward movement than sideways movement. But I think that'd have to be looked at to see where the polymer would have to be to create a zone of no movement.
Yep. Roller, why don't you use bulk mass concrete instead of geopolymer treatment? Which one is cheaper and quicker?
Well, generally speaking, geopolymer is much, much quicker because to dig big holes and pour in a load of concrete takes more time, creates a lot of mess, and normally disturbs the people in the houses. We often have this with insurance companies that in order to do a traditional underpinning, the people have to be moved out maybe for a number of weeks and put up in a hotel. So the total cost is normally a lot more and it takes a lot longer.
Yeah.
But you could use concrete if you wanted to.
You could. I think that's probably the secondary solution now to Geobear or geopolymer, really, in 2025. Helen, the NHPC guidelines does not cover many shrubs, which can grow very large, a number of plants, trees. How do you suggest we factor for this?
I think, well, depending, you have to go and actually measure the desiccation, I think, really. It's very hard to design from NHPC tables when the tables don't cover these type of trees. So I think you have to look at the actual impact in the soil and do a design based on the actual site conditions.
Yep. Thank you, Helen. And Jack, so geopolymer treatment, is it only applicable to fissured clays, which it isn't, but...
No, it can be used in any clay because even if you have a normally consolidated alluvial clay, which doesn't have natural fissures in it, what you tend to find is as the clay dries out, it forms fissures, but these are shrinkage fissures. They're not fissures created through this sort of deposition of the clay. But exactly the same principle applies. A, kill the roots, and B, reduce the permeability. These are the two things that need to be done in any type of clay.
Yep. Joanna, does the geopolymer treatment cause heave?
It does cause some heave, but the way in which the polymer is put in the ground and the technicians who install it have been trained to monitor the lift. So it's important to control the amount of lift. Most properties that suffer from subsidence are sitting at a lower level than they should be. So lift is probably not a bad thing as long as it's not overlift.
Okay. Would you advise putting in deeper foundations than 2.5 meters? Obviously, you have to consider health and safety and cost, but the SI provide evidence on non-desiccated soil at 2.9. Would this be an option?
Well, I don't know really. I mean, we don't generally advise putting in foundations. We generally advise on geopolymer.
Yeah. We're not builders, unfortunately, Jamie. But thanks for the question. So, Io, can killing a tree using chemical means without removing roots still have the tree influence on nearby building?
Well, we don't kill any trees in terms of what we do with geopolymer. We've got good evidence that shows that what we do doesn't harm the overall health of a tree because the amount of fine roots that are actually removed is very small and they're going to grow back next year anyway. So that's why we don't impact the health of trees. But I mean, answering the question, if the tree is killed for some other reason or removed, then you'll get heave.
Yeah. Joanna asks if the geopolymer treatment causes flooding due to the ground not absorbing rainwater like it used to.
Yeah, well, the treatment is very localized under the foundation. So when we do a treatment, it doesn't extend any more than 0.5 meter outside the line of the foundation and extends to depth underneath the foundation in clay soil. So it's not really going to affect surface water runoff in any way at all, really, which is what flooding is.
Yeah. Chris, what about the water abstraction capabilities, risks of mycorrhizal associations?
Good. I don't really know what one of those is, so he'll have to enlighten me.
Yeah, okay. You've stumped us there, Chris.
Good question.
Excellent question. We will come back to you though. Anything we don't get to in this, because we are running overtime, I'll come back.
We'll get back to you with an answer.
Is it easier to simply kill the tree? Stopping the roots will kill the tree anyway. Better to chop it down than weaken the tree, which could controversial.
Yeah, no, I need to address this because it's all the geopolymer does is kill the fine roots. So these are ones which are, generally speaking, less than 2 millimeters in diameter. The main structural strength of the trees from the tap roots, and they are not affected. There's not been any case of a tree being harmed by a geopolymer injection. Our treatment is very localized and very specific, and it's targeting a particular type of root, which is going to grow back next year anyway. Yeah. So I think this is not what happens with what we do anyway. So we've never seen this.
Yeah. There's still about 30 questions to go through. I think we've run out of time. What I'll have to do is, Andy, I'll have to share these with you on a separate file, and maybe we'll try and answer them and share the answers. Well,
we could probably do a group share with all the answers and all the questions, so everyone's got them.
Yeah, I will do that because I haven't read them all, but there's too many to go through here because we are running over by 7 minutes already. So sorry if you've sent us a question. I do apologise that we couldn't answer it right now, but we have to wrap it up. So I will come back to you. I can assure you of that. So I'll be sending a recording of this webinar out. We might not have the answers to the questions we've missed when I send that, but probably within a week we'll come back to you all. So apologies if you've not had that answer. But yeah, there's still 440 people online. So thank you very much for joining us. We've got another webinar coming up. It's not actually launched yet. That's going to be on infrastructure solutions. So maybe slightly different audience, but if you want to join that, which is Andy potentially will be presenting as well. So look out for that. But thanks again, Andy. Appreciate your time today. And,
cheers. Thanks for people joining.
Yeah, thanks everyone, and we'll see you again hopefully sometime soon. Cheers.